So here's the second lecture in this series of two, and I will briefly recall the specialization setup from last time, and then we're going to talk about metric graphs today rather than finite discrete graphs, which is what I was talking about last time, and I will then give some applications of the theory I've been discussing. So let me share my screen in just a moment, and we will go to the notes. All right. So hopefully everyone can see the screen. This is part two, and let's begin. So first of all, let's recall that we started with a curve, algebraic curve, over a discretely valued field. So this is going to be a curve of genus G, where K is a field together with a discrete valuation. I explained what that was last time. You can think, for example, if you want today, about C adjoint T. And we had some notation that R was the valuation ring of K. So for example, the ring of polynomials. And now we want to choose a model for our curve X. So fractor X will denote a model for X over K. And this is over our valuation ring R. And intuitively, you want to imagine that spec R is sort of like a curve, and that we have some smooth fibers and one singular fiber, except really, if R is a valuation ring, it's a local situation. So really, we just have one generic point and one closed point in spec R. And so we really just have two fibers, the generic fiber, which is X, and then we have a special fiber, which I denoted X little k. Little k was the residue field. And our assumption today is that this special fiber is regular. Well, sorry, I want the model to be regular, which I explained last time, and we also want the special fiber to be semi-stable. In fact, I want it to be strongly semi-stable at the moment, which means I don't allow self-intersections like I drew in that singular fiber where I had little loop-de-loops that intersected themselves. I don't want that. Okay, and from this, we can cook up a dual graph. So this semi-stable regular model gives rise to a dual graph. Well, last time I just called it a graph, but it's the dual graph of the special fiber. And just to recall, the vertices of the graph G correspond to irreducible components of the special fiber, and edges of the graph correspond to the intersections or to the nodes of the special fiber. I gave an example last time, so I won't give the example again right now, but you'll see it again in a moment. And I defined a map. I think I actually defined it in the question and answer period, so let me do it properly now. Let me call this map multi-degree, because that's really what it is. It'll just be the degree of a line bundle restricted to each component of the special fiber. So it's going to go from the Picard group of my surface, these are isomorphism classes of line bundles on this model, to divisors on the graph. Okay, and the map simply takes a line bundle, L, to the divisor, which is the sum. So for notational convenience, let me just identify vertices of the graph with components of the special fiber. So Z you can think of as a component of the special fiber or as a vertex, I just take the intersection of the line bundle with that component, and that's the coefficient of z, thought of as a vertex of the graph. And if you're not so familiar with intersection theory on arithmetic schemes, you can just think of this as, I guess it's probably the definition, the degree of the line bundle restricted to this curve. Okay, now, the question we want to ask is, how does this depend on the
We have a
choices?
question, Matt.
Okay.
The question is there a correspondence between principal divisors and edges?
Principal divisors and edges. No, I'm going to talk about where principal divisors come in just a minute. Yeah, that's the next question. So we want to know how this map depends on the choices that we have made or might have made. Okay, and what are those choices? Well, one thing is we chose a model here. That turns out to be a fairly harmless restriction, but I'll get back to that in a little bit. So let's just assume the model is fixed. But what I'd really like to do is start with a line bundle on the original curve over my field K, not with a line bundle on the family fractor X. And so how would this change if I made a different choice? So the answer is like this. So, you know, given a line bundle L in the Picard group of my curve, it might have different extensions. We have different extensions to the model. And how do they differ? Well, because I'm assuming that the model is regular and also, you know, secretly other things like proper and flat, the situation is nice. And what we know is that other choices will differ. So for example, I could choose L prime, which is the original extension I took, this line bundle on the whole family. I could twist it by some component of the special fiber. So I guess at the moment, this is an example. By definition, that means that you tensor with O x of y, the line bundle associated to the divisor y. Now, what happens if you do that? How does the multi-degree change? Well, the multi-degree of this new line bundle will be the same as the old one, but you have to add a correction factor coming from the twist. I mean, intersection theory is linear, so when you take a tensor product of two line bundles, you just kind of add the intersections. And so, I mean, that's where this formula comes from. It's just straightforward. And then we just are intersecting y and z over all components z. So this last z is identified with the vertex of the graph, and y dot z is just an integer. So we have to figure out what this means. And so what is y dot z combinatorially? Well, if z is different from y, so I twisted by some component y of the special fiber. If z is not equal to y, then we're just counting how many intersection points we have. Okay, that's just what it means to intersect two, right? Because I'm assuming it's semi-stable, so the intersection is transverse. So intersection theory is just counting points. If z equals y, then of course you can't do that. But you are allowed to move your one of the things in your intersection by a principal divisor, and the whole special fiber itself is principal because it's defined by, in this case, for example, t equals 0. If I'm in the case C adjoint T, that's a principal divisor on this surface. And so if you think about it, what happens then is you just get minus the degree of the vertex associated to y. So maybe I'll call that v sub y. This is the degree of the vertex on the graph. but you're just counting how many components you intersect, and you have to take the negative of that. So this is just kind of a standard exercise in intersection theory. But what is that? Look, this is a purely combinatorial description. Z intersect Y, that's just the number of edges connecting vertex Z to vertex Y in the graph. And so this is exactly a chip firing move. This is, or dollar firing, however you want to think about it. So this is where the connection comes in to Riemann-Roch for graphs and the kind of definitions I showed you last time. That when we choose different extensions of the line bundle, we're secretly just doing a chip firing move. Now that's if you twist by a single component Y, but any two extensions differ by a sequence of such twists. And so they'll differ by a sequence of chip firing moves, which means that the ambiguity here in defining the multi-degree is exactly linear equivalence of divisors on graphs. I hope that makes some sense. And therefore, we get a well-defined map. It's in fact a degree-preserving homomorphism, which I'll call trop, because this is closely related to ideas in tropical geometry, from the Picard group of my curve to the Picard group of my graph as defined last time. Actually, did I define? I think I defined the Picard group, but that's not supposed to be injective. That just means my pen slipped as I was writing. And the map, so the Picard group of the graph, in case I didn't define it, is the set of divisors on the graph, which I know I did define, modulo the linear equivalence relation that I defined before. So this is what we'll call the specialization map or the tropicalization map. And the point is that it makes sense to talk about the rank of a divisor of an element of pic G, because the rank of a divisor by definition is invariant under equivalence, under linear equivalence. And so the specialization lemma that I stated very quickly last time is that—
We have a question, Matt.
Okay.
The question is, how is this related to tropical geometry?
Sure, let me get back to that in 1 minute.
Okay.
Let me just state this. So our, well, I stated it the opposite way last time, but okay. The rank of a line bundle on the curve, which is, remember, the dimension of H naught of L minus 1, is always less than or equal to the rank on this graph of the tropicalization of L. This is not hard to prove. I'm not going to give a proof, but it's not difficult. It's just really an observation using the definitions, but it has some interesting consequences that I want to talk about. Now, why am I calling it trop? How is it related to tropical geometry? Well, it depends a lot how you think about tropical geometry. And I don't know who's out there watching exactly and what you know. So let me just say it this way. In algebraic geometry, there's sort of two different points of view, right? You can look at abstract varieties or schemes, or you can look at embedded varieties or schemes, things embedded in some projective space or quasi-projective space. And you know, each has their place, and they interact, of course, in certain ways. So it's similar here. I mean, what most people call tropical geometry is an embedded thing, where you start with a variety embedded in maybe a toric variety or a torus or something like that. And you tropicalize, which has to do with, okay, well, I mean, I'm not going to explain all of tropical geometry right now if you don't already know, but because this is Adam, I'll assume you do know. What we're doing here is starting with an abstract curve that's not embedded anywhere. And so now tropical geometry, instead of embedding the curve in some toric variety, we're choosing a model. And that somehow has the, plays the role. That's the analog of choosing an embedding. The advantage is that it's a lot more canonical. I mean, there's not always a unique canonical model, but in most cases of interest where all these applications will be concerned, there is. But in any case, the Picard groups of any two dual graphs of any two models are canonically isomorphic, and that's easy to prove. So this map really is a canonical thing, and it's preferred in some situations to something that depends on an embedding, but it, of course, depends what you're trying to do. One way to say the connection precisely is to talk about Berkovich spaces, which are kind of inverse limits over all models of something or other, and then you compare that to the inverse limit over all tropicalizations. And Tyler, who's hosting this, has some theorems like this, following up on work of Sam Payne and others. And so there's a long story here, but to be brief, that's how it connects. Are there any other questions?
Yeah, there's one question. There's a question about line bundle. Are you assuming that the line bundle is defined over your base field?
Yeah, I am. And we will get to that point in just a moment too. Right. So I don't want to take the time to write this down, but this Picard group of the graph is very interesting. I'm not going to need it in this talk today, but it's actually a finite abelian group. Oh, sorry. Well, pick not would be. So it's a finite abelian group cross Z, where the copy of Z has to do with the degree of the divisor. And the size of the finite abelian group is the number of spanning trees in your graph. So it's a really interesting invariant. One can say a lot about it, but not in this talk. So let's move on. One more thing I wanted to say. So let's assume from now on, and this is purely because I have a lot to say in a short amount of time, that all irreducible components of the special fiber of my model have genus 0. One can certainly say things in a more general situation, but it would require some new notation and new discussions that I really don't have time to get into. This leads naturally, for example, to what are called metrized complexes of curves if they don't have genus 0, and that's an interesting story, but it's not the story I want to tell today. So in this case, then one thing you can say, for example, is that the tropicalization of the canonical divisor class on your curve, right? So there's a canonical line bundle, and one might ask what it tropicalizes to. It should be something canonical, and indeed, it's the canonical divisor on the graph, as defined last time, which plays a role in Riemann-Roch for graphs. So this story is somehow really quite nice. But why is it useful? Well, in order to tell you why it's useful, I first need to discuss the technicalities of base change, right? Because this is all defined over some given discretely valued field. And as someone asked, I mean, I do need to assume things are defined over K. And if they're not, then the notion of regularity is not preserved. I mean, this is the problem, right? So if you make a base change, then models that were regulars now become non-regular. But it's actually not so bad. So the regularity issue is simply like this. So if we make a base change, K prime over K, let's say that's a finite extension. If it's unramified, then you're fine. Everything is still okay. But what could happen is that you now become non-regular and you have to do some blowups. Here's an example. So suppose, just to show you what's going on, remember last time we had this example where our special fiber looked like this. And that was over, let's say, that was the special fiber of a model over C adjoin T. But now what if you go to C adjoin the square root of T? Well, this model is no longer regular, basically because, well, things that used to look like xy equals t, or xy equals u now look like xy equals u squared, or xy equals t now look like xy equals t to the 1/2. And so you have to make some blow up. And so locally, what does that mean? Well, in this case, the ramification index is 2, and all it means is whenever you see an intersection like this, you would get a new component. So that would be ramification index 2. You have to make these local modifications. If the ramification index was 3, then you would get a chain like this. And so what you see is that what's really happening is the following, that what happens to your dual graph is that it gets replaced by a subdivision of the original graph, where each edge is subdivided into E more edges. So let's say E was 2, just so I can draw it quickly. You would have this situation. Okay. So this is not a big deal because it's so easy to understand, but it's a little bit annoying. And it turns out there's a very nice way to deal with this issue that makes everything work out well. And that is to work with metric graphs. And if we think of the original edge lengths as all being 1, then now we want to think of this new graph as having edge lengths equal to 1/2. So the total length of every edge is preserved. We're just subdividing an edge in a length preserving way. And if you look at these as equivalent objects, that's sort of the language of metric graphs, and I'll write G for graphs and gamma for metric graphs. So formally a metric graph means you choose a graph, and then for each edge you give it a positive real length. But you consider two metric graphs equivalent if they have common.
Can you say something about what you mean by ramification when you were talking about you have that when the ramification is 2 or the ramification is 3? Could you just say a word about what that means?
Sure. So we have the maximal ideal in C adjoin T is generated by T, and if you make if you adjoin, let's say you take an extension which contains a square root of T. So you take C adjoin U mod U square equals T or something like that. Now your maximal ideal is generated by T to the 1/2 rather than T. And so that denominator there, the denominator of 2 is called the ramification index. And for every finite extension, you can define a ramification index. Yeah, I mean, I don't want to give a formal definition, but it's just a concept really in this case, in the theory of local fields, discretely valued fields, okay? I mean, the real point here is just that being regular, which is really a necessary condition to do things the way I set them up before.
Is the operation of the Galois group visible? We're getting lots of questions right now.
Is it what?
Is the operation of the Galois group visible in what you're doing?
Yeah, that's right. So the Galois group of K sort of acts on various things in this picture, and that is interesting. But ultimately, we're going to be interested in this talk in geometric phenomenon. And so what we're trying to do is get all the way up to an algebraic closure of K and do things directly there so that we don't have to worry about Galois groups at all, and get things that are more geometric and have less subtle arithmetic information, though that's of course interesting for other purposes. So the reason I'm talking about base change is that I'd like to define a single graph attached to a model that doesn't depend on the choice of a base field at all. But to do that, you need to renormalize the edge lengths in this way that I'm indicating, and look at metric graphs rather than graphs. Does that make sense?
Mm-hmm.
Okay. So, yeah, so to summarize, we have gamma is a metric graph, and there's going to be a metric graph associated to my original model X over R. And the advantage of this is that this metric graph is invariant under base change. Okay, just because I'm defining it, the edge lengths have to do with the ramification index of the extension. And so in this case, now I can look at, now I get a map. So there's more details to check here, but the outcome is I get a map, which I'll still call trop, from the Picard group of xk bar, so you base change to an algebraic closure, to the Picard group of the metric graph, which I haven't defined yet, but I'm about to. Okay, but does everyone see what I'm trying to do? So now I don't have to assume that my line bundle is defined over K. And the reason this is important is we're going to be talking about some theorems in algebraic geometry in just a moment that guarantee the existence of certain line bundles with nice properties on curves, or maybe generic curves or something like that. And, but those things are geometric statements. I mean, they're proved working over an algebraically closed field, and you really do need to take a base change at some point to get the existence of those nice line bundles. And so it's really not enough to work over a fixed discretely valued field. So one needs to get comfortable with this process. It's like going to an algebraically closed field, going from a graph to a metric graph, okay? So very quickly, so I can still get to some applications, let me sketch how.
There's a question about the, does there exist a Picard group of a metric graph? Because you really only define the Picard group, I guess, for a non-metric graph.
Yeah, that's what I'm going to define right now. Exactly.
Okay.
Mm-hmm. Yep. So let me define that. I'm going to do it fairly briefly. So, you know, I could go slower, but I do want to get to the applications. But again, see my survey paper with Dave Jensen for a lot of the definitions here and some examples. So suppose gamma is a metric graph. By the way, some people call those tropical curves as well. Although often a tropical curve, an abstract tropical curve, will have some additional data of maybe vertex weights that represent the genus of those components that I'm assuming are all zero. Or you might allow some infinite edges. These are compact metric graphs that I'm dealing with. So I'll just say metric graph, but it's really, you can think abstract tropical curve here. Of genus G, so genus means the same thing as before. It's the dimension of H1 of your graph, metric graph in this case. The divisors on the graph will be, well, let's just say it's the free abelian group on the points of your metric graph. So the metric graph itself is an uncountable set because we allow now subdivisions, and not just equal subdivisions, but arbitrary subdivisions, which means that any point along any edge can be considered as a vertex now. So I'm thinking of gamma as each edge of the graph is now a line segment, a real line segment, and all the points on that segment are points of my graph. So I have the free abelian group on gamma. So in other words, just like divisors on a Riemann surface, or the free abelian group on the points of the Riemann surface, you do the same thing here. And now what's a rational function? So I'll call this gamma rational functions. So rational function is a map from gamma to the real numbers, but it should have some properties. It should be continuous, piecewise linear, and importantly, it should have integer slopes everywhere. That's really the tropical condition, is that it's piecewise linear or piecewise affine, and along each segment where it's affine, the slope should be an integer, positive, negative, or zero. And to such a function, one can associate a divisor. And the divisor, maybe I'll put this on a new page, the divisor of a rational function is the sum over all points of your metric graph of, maybe I'll write it as ord P of F times P, where what is the order? This is like taking the order of a rational function on a curve. So you're trying to tell if something's a zero or a pole or neither. And for some conventional reasons, I'm going to look at negative here, but it's minus the sum of the slopes of the function at P. And at all but finitely many points, this is zero because you have two outgoing directions at most points. So let me draw a picture here very quickly. So let's say your metric graph is a circle, and maybe you have some points on that circle. So let's call it O, P, Q, and R. And suppose I take a function that has slope 0 from P to Q, slope 1 from R to Q, slope 0 again, and then slope 1 from P to O. So you could try to visualize the graph of this function. It will be continuous and piecewise linear. The slope is, yeah? Oh, is someone asking a question?
There is a question. Can you remind me what slope means in this context?
So it's just a linear function or an affine function, and I'm taking the derivative of that function. So, for example, if the value at R was 0 and the value at Q was 1, and it was linear along that segment, the slope would be 1. And so in this case, the divisor of F, but so I have a function that's it's increasing, then it's constant, then it's decreasing if you're going around the circle, and then it's constant again. The divisor is going to be O plus Q minus P minus
There's still
R.
a little bit of confusion about what this means, what slope means. So the question now is it only well defined up to sine? What happens if three edges meet at a vertex?
Well, the slope is defined along an edge. And so, oh, so sorry, I should have said the outgoing slopes, excuse me. Right, so yeah, you need to choose a direction. So at a vertex, if this is my point P, in the middle here, this vertex, then I have three outgoing directions. I can look at the directional derivative of my function in each of those directions, or just the slope, since it's piecewise linear. And I add up those three slopes. So, okay, and now we can define principal divisors to be the set of all divisors of the form div f for some rational function f. And that, by an easy argument, is actually a subgroup of div 0, the divisors of degree 0. Yeah, so the divisor of any function is going to have degree 0 of any, yeah, divisor of any function will have degree 0, just like in this example, I had 2 zeros and 2 poles. So that will always happen. And the Picard group of the graph is divisors on the graph modulo principal divisors. Okay. And maybe I won't get into it in the interest of time, but I mean, you still have, you have a canonical divisor that's really defined the same way as before. You also have a rank function. You can define the rank of divisors on metric graphs. It's really the same definition I gave last time. It's just that the definition of linear equivalence is now slightly different. We're saying now that two functions are, two divisors are equivalent if and only if their difference is principal for some f. And you might wonder if this is actually compatible with the previous definitions I gave in terms of playing this game of solitaire. And yes, it is. And that's something one can check. Actually, what's not so obvious, I mean, it's easy to see that in the case of graphs, this kind of specializes the previous definition of linear equivalence, but what's harder is to check that the rank is well behaved. So here's the theorem originally due to Hladký, Kral, and Noreen, and then a generalization was given by my student Yi Luo. So if G is a graph, like in the sense of the last talk, and gamma is the associated metric graph, by which I mean make each edge of the graph have length 1 in the metric graph, and D is a divisor on the graph G in the sense of the last talk, then the rank of D in the sense of the previous talk is equal to the rank that I didn't actually define here, but I'm just letting you imagine. But the point is that, I mean, you don't really have to worry about the distinction because of this theorem. So I'm just going to talk about ranks of divisors and not be too specific about whether they're on graphs or metric graphs. Let it be clear from the context. But this is actually a non-trivial theorem. Okay, so you're correct to worry about subtleties here. But the end result is that you can sleep easy at night and there's actually nothing to be worried about in the end. And the specialization lemma works for metric graphs as well. Well, let me just say that R x of L is greater than, sorry, less than or equal to R gamma of trop L, where we compute everything in terms of metric graphs now. So again, it just says that it behaves like the case we discussed last time in more detail. So now I want to actually say what we think.
I have a question. This is
yeah.
my own question. Is it when it's strict inequality?
Yeah.
Is it's understood what the mismeasure is coming from, what the gap is coming from?
No, it could be coming from somehow different places, and you actually don't want to get into that now because it's pretty subtle. So okay. No, I mean, I would say it's in some sense an open question to really understand where the strict inequality might come from. But it's probably an unsolvable question unless you make it a bit more precise. Okay. Any other questions? All right, good. So then let's talk about one application of this kind of stuff. And I'll discuss what's called Brill-Noether theory. So again, kind of a whirlwind tour. So classically, you could start with a compact Riemann surface, which is really secretly another name for a non-singular projective algebraic curve of the type we've been discussing. Has some genus. And you can fix two integers r and d. D will be the degree of some line bundles. R will be a lower bound for the rank. And you can define what's usually called WRD of X. So that's the set of line bundles. I guess to be consistent, I should write it in Roman font, not calligraphic. The set of line bundles in well, let's say pick D, so degree D line bundles on X, such that the rank is at least this number R. Certainly there are lots of classical ways to motivate why one would want to look at this. I mean, the simplest example perhaps is to look at W12. I mean, this is just an example because, I mean, I can't get into tons of classical algebraic geometry here, but W12 is non-empty. Let's assume the genus is at least 2 or something here, if and only if X is hyperelliptic. That's kind of the definition of hyperelliptic, but hyperelliptic curves have lots of special properties. For example, their canonical map to projective space is not an embedding, and all sorts of other things. So we're interested in these so-called special line bundles that maybe have to rank smaller than you would expect for the degree, and interested in knowing, for example, is every curve hyperelliptic? Well, in genus 2, it is. In genus 3, some curves are hyperelliptic, some are not. But in genus 3, you always have a degree 3 rank 1 line bundle. So again, for example, if genus is 3, then it's a theorem that there always exists, or I guess the way I want to say it is that in genus 3, it's a not difficult theorem that W13 is non-empty. Okay, so these are the baby cases of what's called Brill-Noether theory. Brill-Noether theory asks for the general picture here in arbitrary genus. And so if you do a simple dimension count, well, maybe it's not so simple, it depends what your background is. If you do a dimension count, it's not hard to get an expectation for what the answer should be, but it's pretty hard to prove it. So the idea is we're going to define the Brill-Noether number. I'll just call it rho, but it really depends on all of these parameters, G, R, and D. And it's defined as G minus R plus 1, G minus D plus R. And the classical Brill-Noether theorem, and again, of course, there's tons of variants and extensions, and just giving the super classical version here. 2 parts. If rho is negative, then W RD of X is empty for generic X, for generic choice of X. And part 2 is if rho is non-negative, then WRD is non-empty for all X of genus G, of course. And in fact, in this case, rho is the dimension. What does dimension mean? Well, in fact, WRD is an algebraic variety. So that's what it means. Now, what does generic mean here? What does it mean to have a generic curve? Well, it turns out that the moduli space of curves of genus G is irreducible. And so you can really give a precise meaning to this. It means that this property holds for an open, dense subset of the moduli space of curves. And in fact, though, it's enough to prove it holds for a single curve. Even a single curve in MG bar, the Deligne-Mumford compactification, because of some standard semi-continuity facts that I won't recall here, but just, you know, the existence of a line bundle of a certain degree and rank is a Zariski closed condition, and you can deduce various things from that. So the point being, the second statement here is a statement about every curve. First statement is really about the existence of some curve with a certain property. And both of these have counterparts in tropical geometry, and I want to explain briefly now what those are. Any questions before I say the tropical version? Okay, good. So here's the tropical version. So first of all, let me start with number 2, which I inexplicably called number 2 rather than number 1, like in my notes. So here's a theorem that I proved, but this is really just that specialization inequality, plus, okay, one more thing that I'll tell you in a second. So gamma is any metric graph of genus G. And again, you fix R and D. And if the Brühl-Noether number rho, which secretly is rho of GR and D, is non-negative, then there exists a divisor on my metric graph of degree D. It says that's a D, such that its rank is at least R. So that is just exactly the tropical counterpart of the statement that WRD is non-empty. And what's interesting here is the proof is use the classical theorem plus the specialization lemma plus a deformation theory argument, which shows that every metric graph can be realized as the dual graph of some model of some curve. Now, this last part I don't want to get into right now, but this was essentially a known result. I mean, certainly for graphs and regular models, it was known. In the context of non-discretely valued fields and maybe metric graphs with irrational edge lengths, I don't think this was technically known before, but I mean, the tools for doing this were known. So, so what is the point though? So the point is we're starting with a metric graph gamma. Deformation theory actually allows us to produce a curve and a model of that curve, but I'll suppress the model, whose associated metric graph is this one. And we can apply the classical Brühl-Noether theorem to get a line bundle on X, which has degree D and rank at least R. And now we can tropicalize. And the tropicalization of that line bundle is some divisor on my graph gamma. And by the specialization lemma, the rank of this divisor D is at least as big as the rank of the line bundle L. And so we're done. So that's a sketch of the proof. And what's interesting, among other things, is that no purely combinatorial proof of this theorem is known. It's a statement about combinatorics, but it's not known.
There's a question that just popped up. Someone wants to know if there's an analog of the WRD as a moduli space in the tropical setting.
Yeah, there is. And you can even sort of say things about the dimension of that space in this situation. But yeah, I don't want to define it though. Any other questions about this? So I'll also mention it's, you might ask, what about graphs rather than metric graphs? So if I start with a graph, right, the difference, I mean, I told you that rank is compatible on graphs and metric graphs, but there's a subtlety here because I'm getting the existence of some divisor on this metric graph, but I didn't say anything about being supported at the vertices of some fixed model for my metric graph, right? So in other words, the divisor D I just produced might have support in the interiors of edges of my graph G if I realize it as a metric graph. And there's really no way to avoid that because, well, with this proof anyway, because I mean, the line bundle produced by Brühl-Noether theory really is not in general defined over an unramified extension of your ground field. And to tropicalize it, you really are going to have to take some subdivisions that correspond to these ramified extensions, and the divisor really might have support there. And it seems quite tricky to kind of rule this out. And yet it appears to be true, nevertheless, that a similar statement should hold for graphs. But that's a conjecture that I made in my paper on this subject. And it's still open. So just a statement about finite graphs and the existence of divisors of certain degrees and ranks is completely open. Even in rank 1, I should add, where the previous theorem is now known by a combinatorial proof. So there's an open question that if anyone could solve, it would be super interesting. And let me move on to the other part of Brill-Noether theory, which is the non-existence theorem. So remember, this said that on a generic curve, we don't have any line bundles of degree D and rank at least R. And here the analog is we just want to produce a specific metric graph which has a similar property. So the claim is that there exists, for every genus G, there exists some metric graph gamma of genus G, such that if rho is negative, then there does not exist a divisor D on gamma with degree D, little d, and rank at least R. Again, the Brill-Noether number depends on D and R as well as G. So this was something I had conjectured. And I showed that this implies, so this implies the classical Brill-Noether theorem. By a similar argument as I gave before using semi-continuity, or just the part 1 of it. But I didn't know at the time how to actually construct metric graphs with this property. And it turns out that it can be done. And I guess I have 5 minutes left, so let me just say briefly how one does this. So this was first done by Kuhls, Drysma, Payne, and Robiva. And they gave a purely combinatorial construction of graphs with this property. And the ones that work are look like this. So they're called chains of loops. So we have G loops here, G cycles where G is the genus. And we choose the edge lengths to be generic. There's a precise meaning to that, but I won't say now what that means. And what one can do is actually completely classify for this family of graphs, chains of loops with generic edge lengths, exactly when you have a divisor of degree D and rank at least R. And the condition becomes something purely combinatorial having to do with Young tableau. And when you write down the combinatorics of this situation, you find that these are Brill-Noether general in the sense of the previous theorem, that these give the desired example. The analysis of this, so the point is they showed there's some kind of bijection between special divisors, namely ones whose rank is larger than you would expect on a generic curve, and Young tableau of a certain form. And so I think this is a really interesting connection between chip firing, as discussed in the last talk, Riemann-Roch for graphs and that kind of stuff, and algebraic geometry, the existence of special divisors. And the key tool here are the reduced divisors that I talked about last time and Dar's burning algorithm. So all the proofs in CDPR and in many subsequent papers are basically inductive arguments where you fix a base point on your graph, and you consider certain divisors as you pass chips along in this leftward direction. And you study what happens with Dar's burning algorithm and how to make things reduced in the flavor of what I did last time. So of course, there's many more details than I can say in 3 minutes, but it's some beautiful combinatorics that comes in. And I'll just advertise that the kind of state of the art now, it's gone beyond CDPR, because we can now do this for non-generic edge lengths as well. So I just want to advertise some work by Nathan Pfluger. So Nathan Pfluger figured out on this same chain of loops, he worked out exactly when WRD is empty or not. And there's some combinatorial condition, and the point is we're not assuming generic edge lengths anymore. It still reduces to interesting combinatorics. There's a certain generalization of standard Young tableau, which Nathan calls displacement tableau. And if I had 5 more minutes, I'd give you the definition, but I don't. I'm going to wrap up. But you can just look in Nathan's paper. And this has been applied in very interesting ways recently by Jensen and Ranganathan to study general K-gonal curves of genus G. And it's also related to other work of Dave Jensen and others. I think I'm going to wrap up there and just take any questions that people might have.
There's a long question that just appeared in the chat. When rho is equal to 0, one can ask with many possible variants for the number of points in WRD. Do the tropical and classical counts tend to agree?
Right. Sorry, is that a statement or a question?
It ends with a question. Sorry, now everyone's clapping. I got to go back up to it.
Oh.
The question is, do the tropical and classical counts tend to agree?
Yes.
I think the idea is that if you try to do a finite field point count.
No, so in this case, when rho is 0, right, then that is the case.
When rho is 0.
Dimension, right? That means dimension of WRD should be 0, and so it's a finite set of points. So one can count the number of points, and in that case, yes, it's known that the number of points on a generic curve of genus G is equal to the number of points in the tropical version on a generic chain of loops, and they're both equal to the number of standard Young tableau on a tableau that is the dimension. So you take tableau of a rectangular shape, where this direction is r+1, and the other dimension is G minus D plus R. And you're filling it with G symbols, where G is the genus, right? Because rho equals 0 exactly means that the number of boxes in this tableau is equal to G. If you go back to the definition of rho. So you're filling in these boxes with numbers 1 through G so that the rows and columns are increasing. And the number of ways to do that coincides with both the tropical and classical counts of the number of points in WRD. And what's actually neat is that classically, I don't think one has a, well, no, let me take that back. I think one does know this by limit linear series on curves that degenerate to chains of elliptic curves. You can do a similar thing. So that there's several approaches to this, but the advantage here is you get a very explicit bijection with tableau when you do things tropically.
Other questions?